Yeah, that is. I haven't worked in that issue.
Sorry.
All right, looks good. All right, yes, so welcome back. So some people have disappeared, but hopefully we'll be here in 5 minutes. So the first lecture after the lunch, given by our own Olness, who's going to tell us about dimensional analysis. Okay.
And one short note about the tutorial that follows, I put in the chat, he asked that you pull the singularity image. That takes a while, so you might just kind of do that in background. So that's ready to go. But I put it in the chat. Anyway, so this was supposed to be, originally we had scheduled the director, Abe Deshpande, to give you the overview of the IC. Unfortunately, he's away, so he'll do that next week. It's best he do that rather than me. But so I'm pinch hitting for him on short notice. But I thought what I'd do is show you a collection of what I think are sort of interesting ideas that touch on some of the things you've seen today from Yoshitaka and George, and that you'll see later in the week from Bjorn and others. So we'll go ahead and get started. And let's start really simple. Let's go back to freshman physics, and we're going to do simple harmonic oscillation. And so I've got a mass on a spring, and it's on a frictionless table. I'm not quite sure where you buy those, but okay. And what we want to do is to get a formula for the period of the oscillation. Okay, so I've got the amplitude in meters, mass in kilograms, the spring constant. You can work it out from Hooke's law, and you need to combine that into something that gives you seconds. Now, to get all the correct numbers, of course, you've got to do the real math, but just from dimensional analysis, you can put it together and realize that you've got meters, kilograms, and if you combine the M and the K somehow you can get rid of the kilograms, wind up with the seconds, but the meters doesn't fit. No matter what you do, the meters will not fit in there. And so, of course, here's your formula, and you work that out. Sure enough, that gives you a period in seconds. The 2 pi you have to do the real calculation for. But what's sort of interesting is this, right from this simple dimensional analysis, it shows you it's independent of amplitude. And so that's a technique we're going to use over and over again. For this particular case, the fact that simple harmonic oscillation is independent of the amplitude has some interesting physical effects. For example, I teach music and physics, and one of the things, since the frequency is inverse to the period, what it means is that your frequency does not depend on the amplitude. So that means if you're in an orchestra and the woodwinds are playing loud and the brass are playing soft like they should, the amplitude doesn't depend on the frequency. And of course, that's violated daily by middle school bands. But in principle, if you stay within the limits of Hooke law, that works out. And you could do something similar for the pendulum. There you find out it's independent of mass. Again, just some dimensional analysis. So that's sort of a useful technique to see what things depend on and what they don't. And again, connecting back to particle physics, when we look at things like the structure of a proton and the structure of a nucleon, in this case, I have some particle, and I look at it with a particular wavelength or particular energy of light. And if I look at it with a low energy, a large wavelength, or high energy, high wavelength, if it looks the same under both of those, then that's sort of interesting if what it appears to look like doesn't depend on the energy or the wavelength of my probe. That is quite interesting. And when it's independent of resolution, we can make some assumptions about that. So we'll get there in a minute. Let's do one more example. And this is the Pythagorean theorem. And we're not going to do this the way you probably did back in high school geometry. We're going to try something else. So I've got a yellow triangle there. And from the angle side angle theorem, that completely specifies my right triangle. And I want to write down a formula for the area. So the area of triangle C, it's going to be something in meters squared. So I've got 2 angles, those are dimensionless, and I've got the hypotenuse, that's a dimension. So it's got to be something proportional to C squared. That gives me the units. And then it's got to be something else that's independent of, that's dimensionless. The only thing I have to work with, the angles theta and phi, so it's some function. I don't know what it is. I don't care what it is, but it's some universal function of those coordinates. Okay, so that's great. But now what I'm going to do is I'm going to chop this in 2. And I'm going to turn the yellow triangle into a green and red triangle. And I apply the same thing, again, because those are similar triangles. Each of those is defined by a hypotenuse of two angles. And that function, that dimensionless function involves the same two angles. So it's scale invariant. There's absolutely no scale that those are dimensionless objects. And so it's going to be the same f. And now just from conservation of area, I put that together and I get the Pythagorean theorem. So that's kind of cute. But this idea of scale invariance is actually going to be quite important when we go through and start trying to do calculations and things like that. So we'll try that out. So again, this idea of scaling, I highlighted it here a little bit. And in this case, if it looks the same at all scales, then most likely, to the extent we're probing it, it looks like a point-like particle. What would happen if it looked different at different scales? Well, here's one example. Okay, if you probe it with a low energy, long wavelength probe, you don't have much resolution and may look like a blob, but you get more resolution and then more resolution. And hey, look at that, we discovered Peter Higgs. So that's kind of cool. And that's the essence behind the deep and elastic scattering that you're going to hear about over and over again, and really grows out of the antique Rutherford experiment, where he took alpha particles in a gold foil and smashed them to discover that basically the nucleus was sort of this hard core of the atom. And that's what we're doing over and over again, just with different scales. And in fact, here's a shorthand. If you probe the atom at different scales, what was supposed to be atomic, that was supposed to be indivisible. And if you keep it with low energy and long wavelength, it looks like that. But if you start probing it below about an angstrom, then you discover the nucleus, you get out of Fermi, you discover the proton, and we've done something in the order of 10 to the minus 18th meters. And so far as we can tell, the quarks and the electrons seem to be point-like particles. There's some theories that suggest they may be otherwise, but to the extent we've played with, those seem to be point-like particles. So, that you get scaling down to level, and then you discover the substructure and sort of scaling like that. We can take a look at more scaling going outside of physics. I think there's a very fascinating analysis by Jeffrey West. This is pulled from his book. For example, here I'm looking at Kleiber's law. I'm looking at the body mass of various animals versus metabolic rate in watts. And, surprisingly, they outline this universal curve, but it comes in other places. The Reynolds number, you can define a dimensionless Reynolds number, which is useful in distinguishing turbulent and laminar flow. You can do patents versus population, income versus employees, a whole range of things. And when things line these universal scaling curves, it's suggesting that there's some underlying deeper principle going on there. Coming back to high energy, here again, we've got the structure function, in this case F2, versus the X, which is, you can think of that as the momentum fraction of the partons inside of that. And I've plotted this for a range of energies, a range of different Q squares and GeV squared. And all these energies seem to fit on this universal curve. Okay, and again, that's suggesting something to us. In particular, it's suggesting that they're point-like objects inside the proton. We refer to them as quarks. So now, let's go beyond that and let's think about multi-scale problems. And that's going to be a little bit harder, and we're going to see the appearance of logarithms that give us nightmares and lots of work to do. So I've pulled this from the CTEC handbook. And on the top, I've got the E plus E minus total cross-section at 3 loops. So when I look at the total cross-section, I have the energy that factors out into that sigma 0. That's the sort of Born cross-section there. But beyond that, this is 3 loops. I've got, does this work? Oops. So I got to go back. There we go. There we go. Yeah, I've got my alpha S squared, and alpha S cubed. I've got a whole bunch of numbers. They're ugly numbers, but they're just numbers. And so, it's complicated, but not that complicated. Compare that to the case of Drell-Yan. This is a 2 loops only, where that's at 3 loops. And in Drell-Yan, we have both the energy, but I also have a final state mass, M. And so that means I can make a dimensionless ratio. And that's good because the arguments of log should be dimensionless. And now I can have much more complicated objects. And you see, I've got logs and log squares. I've got the various polylogs and also sorts of other complicated things. And that's going to make it a lot more difficult. But again, I can use some of these principles to sort of organize my calculations as I go along. So rather than try to jump into a quantum field theory calculation and trace the logs and things like that and the divergences, let's try something a little bit simpler. And so let's do a freshman E&M problem. And so I have a little bit of a write-up with Randy Scalise, but actually I got the idea from these original papers. So we're going to do something, go back to freshman E&M, but a lot of the concepts that we use in quantum field theory can be derived or can be linked to this. So the problem we're going to do is the potential of an infinite line of charge. Now, you probably did this using Gauss's law. That's great, but we're going to integrate it. Okay, and so just to recap, the potential is the charge per distance. There's some, depending on your units, some overall factor. And here, for an infinite line of charge, I'll use lambda as the charge per unit length. And so I want to integrate this. I pull out the lambda. And if I stare at this, I realize that here, this potential, this is charge for distance. This coefficient in front has the units of potential. So that has all the units of potential. And this integral over here, this had better be dimensionless because, I want potential. I don't want any other units coming in. And I've got the integral. Y is a dummy variable. So I'm going to integrate over y. But when I'm done, I will have a function of x only. And so I want you to write down a function of x. X is, in this case, has dimensions of meters. Write down a dimensionless function of x. That's non-trivial. And of course, the answer is you can't do it because anything you write is going to have units of meters unless you have x over x, which is trivial. And so you're sort of stuck. And the way the mathematics tells us that you're stuck is if you try to do this, you get infinity. Now, as I say here, infinity can be very useful, but this is the bottom line of the problem. I want to write down a non-trivial function of x, but it's there's only one scale. Another way to see the problem is that this is scale invariant. For example, if I rescale x by a constant k, and I work through, because these are dummy variables, I find out that, k times x equals x. So it looks like the potential at one point is equal to the potential at another point. And since usually, the potential difference is proportional to the energy, that's what you use to measure, it looks like anything I do a, delta V, and I'm going to get zero. And so I move a charge from this position to this position, I get the zero work no matter what the potential is underneath it. But now it turns out to be rather convenient that turned out to be infinity. And that's because if I take infinity and add a constant, I still have infinity. But now if I take infinity minus infinity, I don't always get zero. I could get a constant or I could get a constant plus 17. How do I know what's the right answer? What I have to do is I have to regulate that infinity. So when at the end of the day, when I subtract those two, I get a unique constant and I can keep track of that. So that's what we're going to do. We've got these infinities floating around because of this dimensional problem, but I have to regulate that somehow. So when I do this, I get a unique answer. So that's what we're going to do. Now we're going to regulate it two different ways. The simplest way, and the way you might have done as a freshman, is that you take that infinite line and you chop it. So you integrate from minus L to L. And that works because now I have an extra length here, and I could get a non-trivial log. Previously I would have had just log of x, and that doesn't work because x has dimensions. But now I've got two scales, and I can have an argument of the log is dimensionless, and it all works out. But this L, that I chopped off, that's arbitrary, and my physical quantity should be independent of that L in that regulator. And so let's try it out. The electric field is the slope of the potential. So if I work that out, sure enough, I can take the limit and I get the correct answer, same one you got from Gauss's law. And the energy is basically the difference in potential. And here again, you can work that out and you take the limit, and that also works out. Okay, so what have we done? We've solved the problem. trivial function, okay? So the potential depends on this extra length scale, but the physical quantities are independent of that. That's a key element. And we remember that the potential by itself is not physical. It's only when you take a difference of the slope that you get something physical. Great, the problem solved. But when we did this, it turns out we've broken the translational symmetry. And so let me just be explicit for you. If I take this line and I shift it left or right by a constant c, I get a different messy formula, but it's not invariant under that shift. For this problem, it doesn't matter, but in quantum field theory, gauge symmetries and ward identities are rather key in doing the calculation, making sure things cancel. And so that's a real problem. We really want to maintain those symmetries. So what we're going to do is we're going to try a second regularization technique, and this is called dimensional regularization. And so, everyone's saying we should think outside the box. We should think outside 3 dimensions. And so what I'm going to do here is hit the right button. I'm going to take my integral in dy. Instead of doing it in 1 dimension, I'll do it in n dimensions. And if I divide that out, here's the radial part, has units of y to the n, and the angular part, and here's the details on that. You recognize the angular part, here's 2 pi, the circumference of a circle, 4 pi, the surface area of a sphere. That's the volume area of a 4 sphere, et cetera, et cetera. And so now if I do the same thing, but now in arbitrary or in n dimensions, okay, again, this has potential, so everything in the integral must be dimensionless. Well, the angular integral is dimensionless, that's just a number. I have dy over y, that's meters over meters. I have this extra y to the n minus 1 floating around. That's a problem. I need another dimension in the problem. So it's not enough just to wiggle my dimensions from 1 to n. I need another length in the problem so I can make this dimensionless. Okay, and so just like in the cutoff case, I introduce a length scale L. In this case, I'm introducing a new length scale mu so I can keep that dimensionless. I cannot avoid that. Okay, and then I'm just going to do a shift here. I want to go back to n equals 1 dimension. So epsilon measures how far I'm away from 1 dimension. And if I work this out, here's what I get for the potential. Again, this has units of potential, lambda, and then I have x to the power over mu to the power. That's dimensionless. That's why I needed the mu. I get a gamma function of epsilon, where epsilon, I would like that to go to 0. That gets me back to 1 dimension. But here's the gamma function. The problem is gamma of 0 is infinite, and I get a factor of pi. So I get something I can write down, but I can't take that away. All right. But the good news is we've succeeded in regulating the problem. I regulated it by, I'm epsilon away from 1-dimensional integral, but I still had to introduce a length scale. You can't avoid that. Otherwise, you can't have a non-trivial x dependence. Okay. So that's looking pretty good. And this is just a recap. Why do we need the extra scale? Again, this has units of potential. Now I introduce a new scale. I have x over mu. That's dimensionless, and I can build things out of that. If I don't have the mu, I'm stuck. I can't have anything non-trivial. So that's the essence of that problem. So here's what I get for the dimensional regularization. It's up there in green. And again, we want to check. The potential depends on this epsilon parameter, artificial epsilon parameter that I introduced, the artificial mu parameter that I introduced. Okay, so that's very dependent on those things. But I want the physical quantities to be independent of those regulators. So again, the electric field is a slope. So if I differentiate that, sure enough, I can take this limit and I get the right answer. And likewise, for the energy, I take the difference between 2 points, and I also get the right answer. So as I say here, we've solved the problem at the expense of an extra mu scale and the regulator. I've gone epsilon away from 1-dimensional integration, but I still had to introduce a length scale so I could get a non-trivial x dependence. But the translational invariance is preserved. And so that's why we like the dimensional regularization. And for those of you that may have done calculations, we have Pauli-Villar's regularization and other techniques to do that, but they don't preserve these symmetries. And that's one of the key reasons we use dimensional regularization. Let me connect this up to quantum field theory. I'll take the potential and let me expand this in powers of epsilon. Okay, and if I expand it in powers of epsilon, I have a 1 over epsilon, which is, there you see explicitly, I can't set epsilon to 0, I have a singularity. And then I have some constant terms, and then I have some other things proportional to epsilon and epsilon squared. Okay, so this is what I get. Now, if you go and do a next leading order Drell-Yan calculation, if you look in this reference or in the CTEC handbook, what you'll find is this is the answer, the partial answer. If I expand that out, you see that it has exactly the same form. Okay, it has the 1 over epsilon singularity. It has this log with the pi and the Euler gamma and the log of the scales. And the only difference is there's a 1 here and a 4 here because we were doing a 1-dimensional integral. And when you do quantum field theory, you do a 4-dimensional space-time integral. Aside from that, the mathematics is exactly the same. And so, when you open up whatever book and you see the complicated calculations, come back to here, it's exactly, that's the essence of the math. It's exactly the same as that. Let me pause before I go on. Any questions, comments, or things I should touch on? Okay, because I am skipping around a bit. Yeah.
Sorry, but then okay, I understand the math, but then if I were to actually measure the potential, what meaning would the epsilon and mu actually have?
Mhm.
Non-math world, but
Okay, let me try this good segue. This might be. Okay, so I expanded that out, and what I've got in the top is original. And, I've got the potential, but it depends on this epsilon, which is troublesome, and it also depends on this mu. Both of those are non-physical, and I don't want those in the final answer. In particular, the fact that this, if I go back to 1 dimension and I set epsilon at 0, I'm going to have problems. Now, the potential, the electrical potential, usually, that's, we arbitrarily define it to be 0 at infinity. That's convenient because it's 1 over r, or it goes to infinity, but we could define it anything we want. It's like defining height. I can reference my height to sea level, to this room, to the top of the Mount Everest. It's all a reference. Okay, there are different references, but the important thing is when I, take a mass mgh from this height to this height, I can figure out the work from the difference. Or when I take a potential charge from this potential height to this potential height, that difference does not depend on what my reference is, whether I reference 0 at infinity or my shoe size at infinity. So here, what I'm going to do, because I realize the potential isn't physical, I'm going to choose a different reference scale. And I will choose to just drop that term in red. I'll just get rid of that. Okay, I'm going to call this a minimal subtraction term. So that goes away. And then I've gotten rid of that pesky infinity. And that's going to be my potential. Okay, and then somebody else comes along and says, well, this Euler constant, this pi, this appears over and over again. Let me get rid of that too. Okay, and that's somebody else's renormalization scheme. We'll call that MS bar. Okay, and so I've just used different references for the potential, but because that's not physical, I can do that. But we better check, this isn't physical, but the physical answers had better be independent of that. So let's check it out. If I want an energy, I say, if I take the potential in the MS bar scheme at x1 minus x2, you can kind of see immediately that gives me the difference here. If I do that in the MS scheme, if I take the difference, it doesn't matter. It'll cancel out. Okay, and so that's great. So with or without the epsilon, I get the same answer. Okay, and it sure is a lot easier if I don't have to carry those singularities around, especially if we want to try to put this on a computer. But you have to be careful because you can see if I mix schemes, if I do MS bar minus MS, now sometimes I've got that term and then sometimes I don't, you're going to get the wrong answer. So let me come back. Does that kind of help on other questions or comments or? Okay. Let's check where. All right, so brief recap. We found out that the regulator can provide a unique definition of the potential V. I'll get to F, and omega is my shorthand for the particle scattering cross-section. But initially, we used a cutoff regulator. That I chopped it off at plus or minus L. That did the job. Okay, the potential depended on L, but the physical quantities, the electric field and the work, did not. But it wasn't translational either. With the dimensional regulator, I go to dimensions. I go epsilon away from my integral dimension. And what's nice is that does respect symmetries. And when I'm doing QFT calculations, that will respect the translation, Lorentz, gauge invariance, things like that. But I thought I could get away with the dimensionless, adding something dimensionless in there. I still have to put in a mu scale. I have to put in a length scale so I can have non-trivial functional dependence. Okay, but that's okay because the potential is not physical, but all physical quantities, the electric field, the slope, the difference, which is work, and in a minute we'll show you the cross section, are all independent of the regulator. Okay, and so and then you can renormalize them. You can throw away 1 over epsilon. You can throw away a constant. Okay, that's purely arbitrary, but the physical quantities had better be the same, independent of the scheme. Okay, so now let's see if we can go from the freshman physics and connect that up with some of the ideas from what we saw earlier. So coming back to this, when we do our calculations, the mu scale in here was an extra length scale I put into my problem. But if you kind of open up your textbooks and things like this, they talk about the renormalization scale that comes into the cross-section, hard scattering cross-section calculation, or the renormalization scale that comes in the Parton distribution, or things like that. Where does it come from? And where it comes from is when you try to answer the question, what is inside the proton or nucleus? The answer depends on how closely you look. And so it's summarized here. If I look at a large scale, I see there's the atom. It's a little hard billiard ball. It's fundamental. It has no structure. But if I look a little closer, I see, there's electrons and nucleus. Then I see the proton, then I see the quarks. And so if I look at different scale, I see different things. So that was actually addressed by an old preprint by Charles Dodgson some 100+ years ago. So you recognize this from Alice in Wonderland and the interaction with the Cheshire cat. And so Alice says, would you please tell me which way I ought to go from here? That depends a good deal on where you want to go, said the cat. I don't care much where, said Alice. Then it doesn't matter which way you go, said the cat. So long as I get somewhere, Alice added as an explanation. Oh, you're sure to do that, said the cat, if you only walk long enough. And so here, if you don't have an ill-posed question, you won't have a good answer to it. And so if I ask what's inside a proton, I have to define that rather carefully. And so here, this is a cartoon for basically deep inelastic scattering. So I've got an electron that comes along here. It exchanges a photon, and that probes one of the quarks inside the proton. All right, and so this is the whole thing all together. And there's lots going on in the proton. This is a strongly interacting non-perturbative thing. I've got lots of gluon radiations going on. And if you say, well, gee, what does the proton look like? It, just as we saw in the previous case, it depends on how closely you look. Okay, if you look at this scale or this scale or this scale, you get different things. In this cartoon, basically, if you look at this scale, you see 2 gluons in the hard interaction. And this scale gives you 3, and that gives you 4, and that gives you 5. Okay, so what you see depends on what the scale is. And so the challenge with what we work with here, this basically is the this is the kind of fundamental factorization formula that we use for all our hadronic calculations. And essentially, I have an observable at a cross section here that I will measure at an experiment like ERA or the ESE or whatever. And then I have a perturbative cross section, a sigma hat, that I can calculate. And so that's illustrated here by an electron interacting with a quark. Okay, those are all fundamental objects. I can calculate that perturbatively. That works out just fine. But the thing I can't calculate perturbatively is this big mess here, this non-perturbative bunch of all the stuff going on inside a proton, or if it's a nucleus, the EIC, that's what I can't calculate. That's what I can't calculate. So what I'm going to do is I'm going to chop the problem in two parts. I'm going to chop it in two parts, and I'll work out the part scattering cross section, the sigma hat that I can calculate perturbatively. And I will extract, or I will extract or basically measure this non-perturbative stuff that I can't calculate by basically inverting this equation. I go and measure a lot of DIS data at the HERA or the EIC, and if I calculate this and measure this, I can determine the F, and that's the game. But it's not quite so simple because I have to say where I draw the line. Okay, I draw the line here, 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 and if I draw the line in different places, I'm calculating different things. And so that line is going to be my mu. That's my renormalization scale. And it's an energy scale. And basically it says things that are higher energy than this mu, I put those in hard scattering, and things that are lower energy than mu, I put into this non-perturbative thing. And you can see as I slide that back and forth, both of those shift. And that's illustrated here in my formula. Both of those terms on the right-hand side depend on mu, but the experimental cross-section doesn't. So if I split that up in different ways, they'll compensate each other, but the result I get from the EIC should not depend on that, should not depend on how I do the calculation. And so, as I say, the mu dependence must balance, and that's a very powerful technique we're going to use in just a moment. That comes down in the form of what we call the renormalization group equation, which is a mouthful, but in essence, what it comes down to is basically this statement right here, that the physical cross-section does not depend on mu. The physical cross-section doesn't depend on how I split up the calculation to work it out. It better be independent of that. And that is very powerful because that will tell me, among other things, will tell me how this non-perturbative part of distribution will depend on energy. And so let's try that out. And so if you'll give me one page of equations. So we're starting at the top there. I have on the left, here's my experimental cross-section. Here's my non-perturbative part-time distribution. And I wrote this as omega instead of sigma hat because it's easy to lose the hat in this, and that's rather important. So it's the same as sigma hat, but the important thing is this sigma is physically measurable. That's an experimental observable, and this omega or sigma hat, as you like, is something calculable from my theory. Okay, and I've been explicit. The two things on the right-hand side depend on the scale, how I chop them in half, but the thing on the left side does not depend on that scale. It should not depend on how I chop them up to do the calculation. And so the renormalization group equation comes down to the physical cross-section should not depend on how I arbitrarily decide to do the calculation. So that equals 0. And if I just apply the chain rule, I get this. Now, a small detail here, I've got a convolution. Undo the convolution, I had to do a Mellon transform. I'll leave that as homework, but let me just be fast and loose with the calculus. And now I take this and I put all the stuff with F on one side of the pink box and all the stuff with omega on the right-hand side in the orange box. And when you see that type of behavior before, what do? You always set it equal to, set it equal to a separation constant. Okay. That's the typical technique. But what it says is, what's neat about this is this hard scattering cross-section omega is purely that I can calculate that from perturbation theory. This is non-perturbative, perturbative, non-perturbative. But because this is perturbative, I can calculate the separation constant. And because I know the separation constant, I know how this non-perturbative function changes with energy. Okay, and that's the essence of the Decob equation. Okay, that's the evolution equation of the partition distributions in Mellon space, or if you prefer, transforming me back to X space, it looks like this. Okay, and even though this is non-perturbative, I can't calculate that because of this relation, because of this clever observation. I know the energy dependence of this, and that's a key element that we'll use in solving or doing the calculations. And at least in Nolan space, this is very easy. I can even solve this. I can even solve this for the Parton distribution. I find that the Parton distribution, the energy dependence is viewed to, in this case, minus gamma. We call that the anomalous dimension. It's a dimension because that tells you the mass dimension or the mass scaling of the Parton distribution. So hence the word dimension. Anomalous, why is it anomalous? That's because if I had perfect scaling, okay, remember perfect scaling, if it's truly a point-like object, it doesn't depend on the wavelength, it doesn't depend on the energy, okay? And if it had perfect scaling, that would be zero. And the extent to which it's not zero is anomalous. So that's where the term comes from. It's, bit back in the literature, but that's where it comes from. And again, that's the essence of the Dekop equation. And that's basically the key that we'll use in all the PDFs. And again, this, I was hoping to give this later in the school when you've seen a little bit of this, but hopefully it'll come around when we start seeing the PDFs and other things. Let me pause there. Any questions, comments before I go on? All right. And so, I before I showed you an older version of the scaling, but this is the data from a variety of things, including should have some hair in there, but this is the structure function. If I pick the correct x value, in this case 0.2, the scaling is perfect. There's no dependence on the energy. You see, as I go away from that, I get a little bit of variation, and we'll talk about that. I think in George's lecture about the QCD modifications to that coming from the gluon. But in the central value, the fact that this scales perfectly, the fact that this is independent of energy, basically is telling you that there seemed to be some sort of point-like object inside the proton that's giving this behavior. There's the homework of the Milne transform, if you like. And again, just to kind of come full circle, we did the freshman physics calculation to introduce why these renormalization things come in, but essentially this key element, I have to introduce this mu scale when I divide up my problem, just like I had introduced the mu scale to get a non-trivial x dependence in the freshman physics problem. And because that cancels, I can use a normalization group to tell me how this non-perturbative function scales with energy, which is kind of slick. It's completely non-perturbative, very hard to calculate, yet I can say very precise things about the energy dependence because of this balancing act between this perturbative piece and this non-perturbative piece. So and again, I'll flash this, but again, the answer depends on the question, so you have to pose a good question. So I will finish there, and be glad if you want to talk about details or other interesting things this evening. Be glad to look at this. But it was just sort of a miscellaneous collections of sort of ideas and things I thought were interesting and important. So I'll finish there. Thank you.
Great comments. Work you want them to do? Yeah.
What would the generalization be for the EIC, not only deep inelastic scatter?
Well, now you want to go from protons to nucleons. And so now you've got to make some assumptions how you're going to do that. And in fact, I've been working with the NC-TEC collaboration, basically extending from proton PDFs to nuclear PDFs. And there are a number of assumptions that go into that. And in fact, we've tried the simple one is to just do a simple A, making, dependence on the nuclear A parameter. That works. But more recently, we've tried some other things, sort of connecting up to doing a single body, two body perturbations. And that also has done some interesting things. So for me, what I think is particularly interesting about the EIC, it'll have a lot of data. It'll have it very close to the perturbative, non-perturbative transition, and we'll have it for lots of nuclei. So that's a very challenging region to work with. But we'll have a lot of data. We'll have it for different nuclei, so you can try light nuclei, heavy nuclei. And then we don't know how to handle all that. So that's where we need some good ideas. I mean, there are new tools coming along. If you look across the last decade, people have used, boosted decision trees, machine learning techniques to try to analyze jet structure, jet cross sections, things like that. That's been very productive. Maybe somebody with some good ideas applying that to this data can push the perturbative region farther into the non-perturbative region and kind of connect that up. I mean, the EIC is just going to have lots of data in that region. And so I think there are lots of puzzles out there to be solved when we have the data, and data will drive good ideas. So for me, that's what's most interesting about, what we expect to see from the EIC. Yeah. Yeah.
I don't know if you've seen some of the energy correlator measurements that they published from Elise or Star has one too, where they like you take a jet and you take the correlation between the particles within that jet. They see that well, the idea is that they can really see where that transition from like PQCD to non-perturbative to anyway, if you line them all up, because they did take out the energy dependence, they all line up one scale. I can send you something. I don't know if it's the same idea of like you can take the ratio from the third EEC, so from correlation between three things and two. They say they tease out the value of the anomalous dimension, but I don't know if it's
I haven't seen that. That's outside my area of expertise. I like to.
Okay.
I mean, this stuff comes back to, they saw the scaling behavior, and it's pointing to something. What's it pointing to? And eventually they deduce that, hey, this is, there are quarks inside the proton, and then they went another step that they found out when they checked the momentum sum rule. They found out, hey, the quarks only carrying half the momentum. We're missing.
Yeah.
Yeah. So
there's
when you see those relations, it's like it's telling you something.
Yeah.
And in fact, I mean, we just did this, a different parameterization of nuclear PDFs using sort of a monopole dipole type of parameterization. And I think that also is telling us something. We don't know what it is, but we need interpretations. But yeah. No, I like to see that.
I'll send you some of the stuff because what they think, because then you look at all the results from all the different colliders, and they line up pretty nicely. But where that value is, there's discussion, there's arguments on what the scale is supposed to be. So I'll find one from my friend. And
sounds like a good debate.
Yeah.
I will be around this evening, so we can look at this more in the notes. Let us thank. And come back at 2:30. Before we do so, there are 4 students in this room. I need to get keys from me for dorms. Those who need the key, come here and otherwise go and have some.
And FYI, the local Stony Brook students, we had extra dorm rooms, so I assigned them. So if you want to use them, we have a key, you're welcome to use it. You have to return it, but if you don't, we'll just turn it in today. So that may be some of the people that, we had extra rooms, so I just, if you want to crash one night here, you're welcome to, but if you don't want it, we'll turn it back in, so.
We have keys for all students, they will just need to return them after the week.
All right, so I guess 2:30, yeah. And if you would start downloading the Docker image, it's in the WhatsApp, the command, the curl command will pull that down. So okay. Stuff.
Oh, that's why I had some.
Yeah, because we had empty rooms. If they live far away, they might prefer because we are on one schedule. We probably.
Open in spaces.
They are.
We got this
I
far.
think,
One of those games broke mine. You can return it if you want. I would keep it.
I just, I figured if somebody
Yeah.
lives, they live half an hour away.
It's a great idea.
Yeah.
Much appreciated.
Well, they were empty rooms.
Okay.
Saki.
Oh.
Sorry.
Thank you. How are you doing? Welcome. How are you? Do you need to hook up your computer?
Yes, probably. I should
So
probably
talk to Nathan because you have to share your screen and log into Zoom.
So this is the residency.
Meet
One is, so.
You're teaching, right? Okay. Share your screen. Is your, do you have like a PDF or?
It's just in the hassle place.
Slides, okay, can it be a PDF?
Yeah, I can.
Okay, make it a PDF, and then is it on the Indigo or no?
I have it on this.
Okay, email the PDF to that email address.
So.
cfns.media@gmail.
Right.
And then we can open it up.
So.
No, but look at
So basically, what you're seeing there, that difference is coming from the gluon radiation, which has changed scales.
Isn't it got a structure present in, I mean,
Where are you from? Okay.
Yes,
there is some structure.
That's.
yes, yeah, so, right, so if you look here, you say it's independent of Q squared. So if you go here, basically, yeah, there's a Q squared that's coming from that's coming from the gluon,
Try to ask him somebody.
basically the gluon rate, so you've got a cork at 5 carrying 85%. And then if you start to look, you look at that high resolution, you see, oh, that actually radiates a gluon. So that 85% goes into, goes into 10% of gluon and 75% of the cork. And so it, and so it, it'll shift the cork down a little bit. Some of them.
What's this in?
Some of them go down.
He was trying to install it. I haven't tried.
So
The GitHub base and the
well, like,
If that's what he's
Yeah,
probably.
maybe you.
I think George is one. That's the effect of the one evolution on. But it's a logarithmic effect.
Oh, you haven't figured it out.
Yeah. That's why, before they had Hera, they were in small slice. Really hard to see that. Tell me your name again.
I'm Arjun.
So I.
Thanks.
Okay. Oh, the class. Okay, all right. I'm saying this. Okay, sure. It was only. I'm starting the. Currently trying to. When I started that. Yeah. Right. And I. The. Focused on classes. Basically split my.
I mean, I use. You use.
Yeah. And they studied a lot of. Because basically.
For the.
As a physicist, I but when I started, yeah, there was fun. That's understand. And if I don't understand the math, I can't do the same. So I don't think I can pick up this to you, but I read the paper. The sentences are oxymoron, I mean, they don't make any sense. Right?
We are reading.